We think it's good? Okay, so we can start. Maybe it was so bad. You all say, Laurent, you were saying it's very noisy, you can't hear properly. Clara, Charlie, you said you had a lot of distortions. So maybe you didn't hear what I was trying to say. This web TV lab setup, we have chosen it to really show to you the nature of the news of the week on our side. This topic of data converters working at microwave frequency from the lowest band up to Ka band. We had talked about that on paper and in some presentation, but we had never shown hardware. That is the news this week. We have working hardware, and that's the whole purpose of these demonstrations. So you acknowledge, Charlie, thank you. You can hear us better. And Clara says it's better, so good. Thank you for that. Sorry about the technical issue we had. We run these sessions all day. It's the first time we have an issue, but we'll avoid that. Apologies again. Before we start, I'd like to say, when you watch the performance measurement, we will show you, pay attention to the x-axis, the frequencies. We're very happy to take a data converter, an ADC, with such a high frequency at the input, without any frequency converter before, and even in single-ended, as we will show. We're very proud about that. That's it's been a lot of work to make it to come to the point where we have working hardware and be on the way to release the standard products for you to use in your next generation system. We're very excited, and now I will step on the side to act as a moderator to answer your questions. And I will leave the floor to Romain and Stéphane to run the demonstration for you. Thank you. And send us any question anytime during the show.
So welcome everybody. So my name is Stéphane Bress. I'm an application engineer for the signal processing solution business unit. I'm supporting both analog to digital and digital to analog converter. And I'm also part of the support for EasyStream, the serial interface protocol of communication used on the latest Teledyne E2V data converter, like the EV12 PS640. We will show you on the demo today.
So welcome, good afternoon and good morning for where we are on the planet. My name is Romain Pilar. I'm also an applications engineer as Stéphane. We are working closely together. We are very pleased to have you live on this session with us in our reconstructed lab here, the Web TV lab. So we are focusing this session on the proof of concept that we have developed in order to stimulate our roadmap moving forwards from where we were and where we are going to with our future generation of products. So this focus on the EV12 PS640 proof of concept, what we would like to propose is to watch a video so that you have an introduction to this proof of concept, and we'll be back right after to answer any of your questions that you have. So let's see you later.
Good morning and good afternoon, everyone. My name is Stéphane Bress, and this is my colleague, Romain Pilar. We are application engineer at Teledyne E2V, and we are here to introduce for the first time the latest Teledyne E2V analog to digital converter. This component, the EV12 PS640, is a proof of concept built to validate and anticipate our future development and to execute our strategy towards direct microwave digitization. This device is composed of an organic substrate and of 3 dies. 2 EV12 AQ600 dies, which is an already existing product, and 1 dedicated front-end sampler, which is a new development. This device takes benefit of co-design techniques as well as in-house assembly capabilities to enable direct sampling of wide input bandwidth analog signals of 30 GHz. This is the first step before the next generation of wideband analog to digital converter to extend the performance of broadband satellite communication, test systems, and spectrum awareness system, to name few applications. So, Romain, what can you tell us about the setup we have in front of us? What do we have on this board?
Sure. So we have two boards, as you can see. One is the FPGA board that is collecting the data coming out of the A to D converter. Here is the FPGA, so Kintex UltraScale KU085 from Xilinx. This board is the data converter board. So you have the EV12 PS640 under the fan here. On the board, you have two main connectors, one for the input clock and one for the analog input signal. I have to notice here that for the first time, we are introducing a data converter having single-ended inputs in order to ease the interface with the RF systems, to facilitate its integration into the 50 ohm, the classical 50 ohm characteristic impedance system. In order to evaluate the A to D converter, we have equipments provided by Rod & Schwartz, so two signal generators, one for the clock signal. We are using a clock signal up to 12 gigahertz, and a signal generator for the analog input, so up to the Ka band. Between the two boards, there are 16 coax cables in order to send the digital data between the A to D converter to the FPGA. So these links are the high-speed serial lanes supported by the EC-Stream communication protocol with data throughput up to 12.8 gigasamples or gigabit per second.
So Romain, now that all is set to run the analog to digital converter, can you show us some performance over several frequency bands? For example, C, X, Ku, and Ka band.
Sure, no problem. But I have to first let the audience know that for the clarity of the demonstration purpose, I have pre-configured the device. By pre-configuration, I mean offset, gain, and phase delay adjustments of the internal A to D converter, the EV12 AQ600. Also, some sampling delay adjustment between the two dies. Let me first introduce the user interface here, on which, so this is the acquisition tab, on which you have to configure the clock frequency. Here it is set at 11 gigahertz. This is the number of samples per core used for the fast Fourier transform analysis. This is the input signal that is used for computation of performance. And this is the selection of measurements coming out of the different cores. The plots can be visualized in time domain, as you can see here, as well as in the spectral domain, in the frequency domain. So here with the Nyquist zone extending from DC to 5.5 gigahertz. So here the first frequency at 7 gigahertz is generated by the signal generator, and we can see here the plot folded back into the first Nyquist zone, so with the fundamental tone at 7.05 gigahertz, and you can see the second and third harmonics of the signal. So I can show you some performance metrics. For example, here in this table, you can see the SFDR or spurious-free dynamic range around 48 dB relative to the carrier. Also, the SNR is plotted here, 30 dB, 37 dB. Now I will move up in the frequency to show you the X band, so around 10 gigahertz. Now I've changed the frequency on the signal generator at 10 gigahertz. You can see here the input tone at 10 gigahertz. Just to realize the time domain signal. And in terms of spectrum, here you can see the fundamental tone has moved here at 1 gigahertz, so folded back from 10 gigahertz. You can see here the second harmonic at 55 dB from the full scale. In terms of performance, the SFDR is still around 48, 49 dB relative to the carrier. Now let me move to a higher frequency in the KU band. So in the KU band, the input signal is here 12.1 gigahertz. The acquisition is launched. Here is the spectrum. So you see the update of the fundamental tone folded from the 12.1 gigahertz with the harmonics, again, H2 and the third harmonic at 58 dB relative to the full scale. In terms of performance, the SFDR here is around 52 dB relative to the carrier. Then I will move to the KA band. So in the last frequency I will show is in the KA band, so with an input signal at 28 gigahertz. So here the acquisition is launched and the spectrum plot is shown here. So you have the fundamental tone here folded back at 5 gigahertz and with the harmonics, a third harmonic making the spurious-free dynamic range of around 54 dB relative to the full scale. In terms of performance, I can show you again the SFDR. So the SFDR is around 48 dB relative to the carrier. We have an SNR of still 34 dB, a total harmonic distortion of minus 47 dBc.
Thank you, Romain. You have presented a very exciting analog to digital converter. This is the first Ka-band sampling analog to digital converter on the market. Of course, this is a proof of concept at this stage, but the team is already on track on the development of the next generation of products based on the lesson learned from this concept. To summarize, we have the first proof of concept analog digital converter capable of sampling microwave signals directly in the Ka-band. This will dramatically simplify future wideband communication system or RF test systems. Thank you, Romain.
So, welcome back to the Web TV studio, live from Grenoble. We now have one question from Charlie. Charlie asks, does the EvanKit support continuous data recording?
So the answer is no. We are recording or we are acquiring a burst of data to display in real time or in the spectral domain the data.
So currently with EvanKit, there is not the possibility to record continuously the data. It works by burst.
Yeah, it's a limited number of data recorded by burst. Yeah.
Thank you, Stéphane. For the moment, there is no other new questions.
And maybe to complement, this is what you can see here behind us. You can see there is the update of the spectrum each time there is an acquisition. So every burst of data that are sent back to the computer, they are displayed.
Okay, so still no new questions for now. Please do not hesitate to send questions, comments. We will take them all live and address them. In the meantime, Romain, Stéphane, we know the classical questions and concern that customers or system designers have when they think about using this type of ADC. Mm-hmm. Can we comment or develop on some of those questions that we typically see from customers?
Sure. Maybe we have prepared a slide deck in order to address some of these typical questions. So, what is, Stéphane, the architecture of the EV12 PS640?
So yeah, the architecture of the eVTOL PS640, so it's a multi-chip module composed of 3 dies, 2 eVTOL AQ600. We can see them so on the image at the bottom right, and yeah, so this is at the bottom right. We can at the bottom left, we can see a block diagram of the architecture. One thing, or several things we can emphasize is the eV12 PS640 proof of concept offers single indeed input both for the analog signal input and the clock input. So this will ease the use of this device to match 50 ohm
environment.
Thank you. But there is not only this benefit. We also the front-end sampler, which is the third die, also provide a clock and signal distribution circuitry to provide a signal and clock to the 2 dies, the 2 ADC dies just behind. In the future, this is the first step before the next generation of ADC. We will, and so the development is already on track, to replace these 2 dies composed of 2 AV12 AQ600 by a new ADC dies to meet our targeted specification, like the wide input bandwidth of 40 gigahertz.
Thank you, Stefan. We have 2 new questions. Charlie, I think, Charlie, you're asking a question that is related to the previous one. You're asking, is this going to be supported in the future? I assume you're asking about the continuous data recording. That's the assumption I'm making. Stefan, what do you think? In the future, can we be able to support continuous data recording, or do we think that there is anyway an excessive amount of data flow and we won't be able to do it? What's your opinion about that?
So there is a huge number of data to acquire. So the interface between the logic device, the FPGA, and the PS640 is made of 16 high-speed serial lane with a data throughput up to 12.8 gigabit per second. So here the demo run at 11 gigabit per second. So it's a huge amount of data. So it depends how long we want to acquire data. If we can avoid some data, maybe it will need to embed some digital processing to reduce the number of data to acquire. So for now, we don't plan to do this, but maybe we can help you with this development and give you some
I think that's a very interesting question, Charlie. Maybe if we can get in contact later and understand what your intent is and think about how we can change the way we do it to get closer to what you're expecting. That's a dialogue we would like to have in an offline conversation, if that's possible. We have the second question. The other question from Utelsat is, what would be the maximum instantaneous bandwidth in Ka-band?
So concerning this, the eV12 PS640, so here you can see the maximum behind us. So you can see the maximum instantaneous bandwidth with a clock input at 11 gigahertz. So you can see here basically the Nyquist zone corresponding. So extending from closed DC to 5.5 gigahertz.
So this is a full Nyquist zone we can see on the screen.
Yes, and this is just for an input tone or input continuous wave of at 28 gigahertz generated by the signal generator, and you can see the full spectrum and folded back into the first Nyquist for to show the H3, H2, and other spurs. For this proof of concept, again, this is a very first, let's say, device that we have in our lab. This is in the early phase of its characterization. We are learning from that. We have extracted some parameters already at 10 gigasamples per second. For the video that you have seen and the demo that is running in front of us, the sampling rate is 11 gigahertz, so 11 gigasamples per second. But the capability of the A2D converters that are the EV12 EQ600 and the microwave sampler is above 12 gigasamples per second. So in order to achieve instantaneous bandwidth
of 6.
Up to 6 gigahertz.
Okay. So to answer the question from Eutelsat, Alessandro or someone else who's behind, the NACRI zone can be as wide as 6 point something.
Yes.
Which means if you assume an instantaneous signal, a useful modulated signal with some guard bands before and after near the edges of the NACRI zone, that might be something like 5 gigahertz instantaneous bandwidth can be managed with that.
And in the future generation of products, so we'll embed digital features that will help also to reduce the data flow and reduce, if necessary, the instantaneous bandwidth in the band of interest.
And maybe we can add, if we also use this digital down converter feature, we will also reduce the number of lanes to interface between the logic device and the data converter.
Okay, thank you, Stéphane. There's a new question still from Eutelsat. Is there a level compensation to equalize the 5.5 gigahertz bandwidth? What about phase? Is there a level compensation to equalize the 5.5 gigahertz bandwidth? What about phase? Is it something where we can help on the ADC side, or is it to be managed in front of the ADC? Maybe we didn't really emphasize, but this is a single-ended input, so maybe that's going to help to distort less compared to what is done with today's gigahertz class ADCs. We force today with previous generation of data converters, people are forced to go from single-ended to differential, which really is not helping on this question.
Yeah.
The single-ended input can help. How can you comment on that, Romain?
Yes, for sure. The single-ended input can help to have a better interface between the front end, the RF front end, and the microwave sampler that is in front of the A2D converter. There is no particular in this proof of concept. There is no particular compensation, phase compensation. But maybe we can rediscuss this. And maybe there are some interesting features that could be inserted in the next generation of product. The next generation of product is at this early stage of its development. So maybe there are some possibilities to improve the design and integrate some specific functionalities that would help you to better implement such kind of device in your future systems.
Thank you, Romain. I think for colleagues at Eutelsat, I think if we can maybe have an offline conversation on a call, we can dive a bit more into this question from you and then take it into account later in how we write our documentation, our application notes, and suggestions and reference design to address this point, either with circuitry in the signal chain before the ADC, or in certain ways of implementing the ADC itself.
And we'll also characterize more and more the device. So again, this is the early stage of its characterization. We'll have some more data on the input bandwidth curves versus the input frequency. So we'll see how the variations, the ripples are present or not into the band. So I think this kind of information would help to better understand the behavior of the product in frequency.
Thank you, Romain. There's a new question from EP. what about inob and accuracy? What can we say about that?
So maybe if we can switch again to the screen, we can see here with a single tone, so a continuous wave at 28 gigahertz. So this is the mode. So with the SFSR at -6 dB relative to the full scale, so the output of the A to D converters. The SFDR is 47, 48 dB related to the carrier. And the SNR is 33 dB, which translates into a 5 bits of inob, or 6 bits relative to the full scale. So this is at 28 gigahertz. Of course, there are some variations over the band.
So we have a single tone at 28 gigahertz here, and that's the measurements we have.
Yes, that's the measurements of real life that you have in front of you. And during the video, they are different.
You know, what's the input power of the signals?
So the input power of the signal generator. I have to check on the generator. So here it's a bit higher than 0 dBm in order to have the -6 dBFS at the output of the A to D converter.
Right. So maybe it's worth when we pause a second on this. You see a live performance measurement, 6.2, 6.3 bits of inob with a single tone sine wave at 28 gigahertz, and the power coming into the ADC in single-ended is just slightly above 0 dBm.
As you can see on the demo, this is the top one is the signal generator for the clock signal. It goes straight to the board on the connector that you have at the forefront. And the second signal generator, so this one is the 40 gigahertz signal generator from Rohde & Schwarz. You can see the output coming directly into the single-ended input of this connector, the connector on the board, that goes straight to the input of the microwave sampler, and so straight from out to input.
Great, thank you, Romain. So EP, I hope this answers your question on inob and accuracy. If not, keep asking questions, additional questions. Anybody? So far, I have no new questions. So any of you at any time, you can send other questions and comments, and we'll take all of them. In the meantime, while we wait for new questions, are there some other classical questions we expect system designers to have when considering this type of ADC in their next system?
So yes, so a question is how can we evaluate this device? So we will provide an evaluation board. So if we can switch to the slide, I can describe the future evaluation board. So it will be available in Q1 2021 next year. So this will be an FMC Plus mezzanine board to be interfaced with already existing FPGA development board on the market. Or we will also provide FPGA carrier board to plug this mezzanine board on. So you have a mezzanine board only embeds so the product, the proof of concept EV12 PS640.
Thank you, Stéphane. We have a new question coming in from EP. Actually, it's two questions in one. Do you have multi-channel ADC? The answer is yes. At low frequency, we have a 4-channel quad-channel ADC. It's a quad 1.5 gigasample, working up to C-band. This first K-band ADC is a single channel. In the form of proof of concept today, and also the first version will take to production, industrial production, will be a single channel. However, you need to be aware, and I'm saying it now to answer your question, EP, these type of data converters, they will be available in different forms as a standalone components, regular package ADC that you can put on the PCB next to the FPGA. But the other form we want to deliver this is integrated inside system in a package with FPGAs, either Xilinx FPGA or NanoExplore FPGA, integrated together. And there, when we integrate in system in a package, we can put several of them inside of it. Therefore, you will have multi-channel capability. We will have to think carefully whether both you as the user and us as the maker of the system in a package, we are going to have to be very cautious about crosstalk issues as we go so high in the frequency domain, concentrating multiple channels quite close to each other to a single component at K-band. We have to be very cautious about crosstalk, but I think it can be managed if the number of channels is not too excessive. You have a second question, which is what about thermal dissipation? Today, thermal dissipation on the proof of concept is pretty high because this proof of concept device is not power optimized. We are close to 15 watts, I believe.
Yeah, 14.6 watts.
14.6. This is a lab sample just as a proof of concept. It is not what you will have in production. In production, we will divide the power consumption by 5, approximately 5. So we want to completely change the order of magnitude of power consumption. The production device we will deliver, that's about a year to a year and a half from now as samples. We target a power consumption brought down to per gigasample in a range of 200 to 210 milliwatts per gigasample. Then you can multiply this by the sampling rate you wish to use. It gives you an idea of the power consumption you will have. Maybe Romain, you want to show something?
Yeah, maybe just to to show you the environment in which we are here in this room, using the fan that is on top of the device, so you can see the temperature of the converter. So we are around 70.5, 71 Celsius degrees.
So Romain, this is junction temp.
Yes, junction temp. Yeah, okay. This is a diode junction temperature.
Oh, and if we would be in the other web TV studio, we could put the infrared camera on this, and we could show you the temperature at the top of the package.
Exactly.
That's in the other web TV studio for the other show. We don't have it here, unfortunately, but we'll try it next time. We don't have new questions on the chat box. Maybe Romain, Stéphane, there are some other classical questions we expect from system designers about to use this ADC.
Yeah, so again, if we switch to a slide, we can discuss about the data interface of this proof of concept. So for this proof of concept, the EV12PS640, it requires 16 high-speed serial lane supported by Easy Stream and running at a maximum of 12.8 gigabit per second. We provide a dedicated receiver VHDL designed for the EV12AQ600 on the website easystream.com. So this proof of concept embeds two EV12AQ600 dies. So it will require to use two instances of this design example. Of course, for the next generation of ADC, we will change. We will also improve the data interface. To reduce the number of lanes, we will introduce new revision of the EasyStream protocol using, instead of 14/16 encoding, 60/64 encoding to increase the efficiency, and on this future device reduce the number of lanes to 11. We will also, of course, provide receiver VHDL design example on easystream.com to ease the development and the integration of this device and the interface with a logic device like FPGA.
Thank you, Stefan. We still have no new questions. Anybody in the audience, feel free to, again, submit questions or comments. We'll address them. Are there other typical questions we expect that we can, from designers of system using this ADC, that we would like to address today?
Yeah, maybe if we discuss of the material needed to run this proof of concept. Maybe Romain, can you describe
Sure.
what is available?
Yeah, sure. So as you have seen in the video, or as you can see here in front of us, we are using signal generators for the clock signal. So this is typical equipment that is used in our lab for the characterization, but also for the test and validation steps of our devices. Of course, on the market, there are existing surface mount PLLs in order to have a better integration level, obviously, using standard parts available from standard manufacturers. So there are some examples here on the screen of integrated PLLs with integrated VCOs. There are also oscillators that can be used on this input. And maybe one thing to emphasize, and this is shown on the bottom of the slide, there is no need of external balloon. For the first time, we are introducing a device with a single-ended input in order to facilitate the matching to the 50 ohm classical characteristic impedance of the RF systems, and especially at such high frequencies in which the device is working up to the Ka band. Most of the devices available in the front end are single-ended. So yeah, this is for the equipment, the materials that is needed. Also, maybe one thing to mention is for one of our evaluation boards that we'll provide. So there will be a PLL that will be mounted on board the board from commercial PLL.
Thank you, Romain. Should we make the final conclusions? We have no new question, or is there another typical customer question you'd like to address? Or I think we covered most of the points.
Maybe is there a need to have a mixer?
Good question.
To down convert?
Good question.
So the answer is no. This is,
no,
as you can see,
as long as you work at 2K,
yeah,
you don't
of course.
need it.
If you work in the Q or V band, you will probably need something. But here you can see that straight out from the signal generator, the device is capable to sample directly the signal up to the Ka band.
So that's the great news. Up to Ka band, frequency down conversion or DOCONs are no longer necessary. If the system works at higher band than Ka, we need frequency down conversion, but certainly less stages of down conversion.
Yeah.
That's a cost saving and multiple benefits.
Yeah.
And maybe that leads to the final comments. With this type of data converters, the ADC working up to Ka band here, and the matching DAC, which we have shown on the previous demo, and we will show it again tomorrow, working up to Ka band. The idea here is that we want to create the components that will help you create your next generation of system with a lot more softwareization of RF than what was possible before. We just make ADCs and DACs and semiconductor components. We don't make the system. That's your expertise. That's what you know how to do. But we want to bring the building blocks, the components that will allow you to do some very disruptive next generation of systems. That's really what we are investing our R&D for. And I'm very excited about the 2020s. It's just a year number one of the 2020s. It's been hard with COVID, but technically we have some interesting things coming up. It's very exciting. And we are very much looking forward to work with you on your various projects. We hope that we will we'll have a privilege to deliver this technology to your systems and help you softwareize VRF across the industry a lot more, whether it's for space systems or other systems on the ground, airborne systems, industrial systems, test and measurement instruments like these ones here. I think many applications can benefit from that. We don't even know exactly the full list of applications that will benefit from a lot more softwareization of RF, but I think throughout this decade is going to be very, very exciting. And the type of perspective it gives is quite fantastic. Think of the satellite system. Today, one satellite does one service in one frequency band. This type of technology, as we mature this, as we deliver them, we start to do it now. The hardware is working now today, and other companies will also continue their innovation in the rest of the signal chain, all the way to the antenna. That really makes it possible to think of satellites which is one spacecraft with one payload, but the frequency plan, including changing band, can be defined on the software side instead of really being fixed in a rigid way in the hardware side. That is extremely interesting. But not only the frequency plan, also the type of waveform, the type of service. With so much softwareization of RF, we can think of doing system which can provide a communication service, or with the same RF signal chain also do Earth observation with synthetic aperture radar waveforms, or maybe some of the service around RF. One hardware, many service. I hope this is the future of possibilities that we are opening with this type of technology. Not only us, but all those who provide building blocks in the signal chain, and your talent as well to design this system throughout this decade. And I really hope we're going to have an exciting year, a few exciting years ahead of us. And no new questions or new comments. Last point about these shows, these demonstrations. I hope it's been useful for you to see this in this setup of a web TV studio. It allows us to show different close-up and show us different screen from the measurements and all of that. We will redo these shows tomorrow. If you want to suggest to your colleagues to join, we run the same show with the same demo with the ADC, with the DAC tomorrow morning and afternoon on the same channel. And on the other web TV studio, there is also the processor demonstration. That is quite interesting. We show the power screening capability that we can do on the big digital components, such as a quad-core microprocessor. You can source a quad-core processor from the original manufacturer, and sometimes it's high power consumptions. We can screen them with lower static power consumption. And the other demo with the infrared camera is going to show you the difference. We have two motherboards, same hardware, same processor, but one processor is power screened, the other is not. There is quite a significant difference in power consumption and temperature. That's what you can see on the other demo. It's run by Thomas, and Thomas will also be able to answer your question and explain all the insights into how we achieve this power saving with the same hardware. People don't have to change their operating system and their algorithm. They keep the same. We just provide the parts with less power consumption, and everybody benefits from that. There is also another demo run by the other Thomas on the full flight electronics ecosystem, from the hardware to the software. And also the colleagues from the manufacturing services run a webinar, a live webinar with live question and answers like this on our capability to do system in the packages. Capability and industrial capacity. There is news on that. We are investing for that. It's part of the format of delivery of this data conversion technology. They will come as standalone component, but also as chiplets to be integrated in system in a package. So I also recommend the webinar from the colleague Frederick and Nicholas on the other web TV studio, where they can give you a lot more details, and you can challenge them with any questions you like. We still have no new questions, so maybe we can conclude this demo session. I hope it's been beneficial for you, and I really want to thank you for joining us. Thank you for taking the time to be with us, and I hope to see you soon. Thank you very much.
Have a great day. Bye-bye.
Thank you. Have a good day. Bye.